What I'd like to do for the next couple minutes is to go over hardware and systems section for the neuromorphic computing. This is going to be a really quick overview just to, again, to set the stage. And again, there will be more detailed discussions throughout the rest of the week. So to give you an overview, what I'd like to start is with a larger picture. And here's actually a map of the strategy and approach. People don't remember facts, people remember pictures. So again, this is as simple as possible, I hope. So the way I've tried to structure this is there's actually a numeric order to this. There's an existence proof. There are two key functions, three potential ways to build what we're going to talk about, and two things to do with it once we've built it, and there's one question at the end. What I'm going to talk about for the next couple minutes is just the ways to build it, basically the hardware and systems point of view, and I'll get into more detail on Wednesday for the rest of the diamond pattern here. So how could you actually build a neuro-inspired or neuromorphic computer? So there are three ways to do it. I'll go through them one by one. Again, these are really intended to be just generic, broad categories. They have significant overlap. One way is to do it in software. It's really to use algorithms, clever algorithms, remapped algorithms on very fast machines and simulate brain activity. And again, this is being very commonly done in projects that are in the US, worldwide, in Europe, human brain projects. Actually, what Karl-Heinz had mentioned earlier in terms of deep learning, what Google and Facebook and everybody else out there is doing is really exactly that, implementing algorithms, new approaches on conventional digital machines. Now, the second way you can build a neuromorphic system is on tweaked hardware, what I've called tweaked hardware, basically taking conventional digital systems and then combining them with either novel devices or sort of hardware, digital analog sort of combined systems, and use those to specifically accelerate certain functions that are sort of bottlenecks in what you would call kind of the first software approach. These include specialized GPUs, ASICs, and again, integration of novel devices into CMOS, and sort of neuromorphic hardware that Karl-Heinz mentioned earlier. Again, these still leverage a lot of the existing infrastructure that we have for conventional electronic systems, but they still, at the core of them, have digital components, things that we would normally recognize in how we do our computations. Now, a third way to build a neuromorphic system, I'd argue, is actually a completely new substrate that actually functions the way that neural systems do, in a sense that they do the sparse hierarchical spatiotemporal functionality inherently in the hardware themselves, and they're not just simulating what a neural system might be doing. So again, there are great sort of gradations of how this can be done. This is not to say that these systems won't be digital or they won't have analog components, and they will still have registers or whatever you want to do in sort of for your local computation, but the way they are interconnected, they'll actually behave more like what the neural systems are able to do in terms of their massive interconnectivity and reconfigurability, and potentially provide the low power that's needed. Again, those substrates, these new devices, potentially would allow us to do the liquid state machines and reservoir computing kind of approaches that people have been talking about and have been very excited about, but those seem to be currently limited by power and time when they're implemented on conventional machines or even on tweaked hardware. There are still certain functional, physical limitations in what those systems can do. So This is actually from the discussion at the Heidelberg workshop, and again, in our discussions with colleagues in the field. This is specifically from a project that colleagues at Intel had done, really looking at what would you do in terms of applications, and then you go to the other end of the spectrum. There are devices, some novel device, and if you really try to reach all the way down from your device to an application, or from application all the way down to the device, that's really too far to bridge that gap. So what was done was to actually describe a computational primitive, saying how would this system do computation, and then from that point reach up to applications or reach down to devices, and that provides a common sort of starting point to be able to frame some of these projects and approaches. So going into a little bit more detail, this isn't really intended to be human readable form. Just to let you know that in terms of the discussions, interactions going on for the hardware and systems, there's more material that's coming together to be able to describe pieces that you would need to put together a system like this. For example, what the categories here are: neurons, axons, dendrites, synapses, so things that you would see in a neural network, in a biological neural network, how you might be able to describe it. And there are ways of implementing those functions in an electronic format. And then there are notes on how you would go about doing those interconnects, and what some of the challenges or what some of the benefits might be for such an approach. So I'd like to very quickly conclude, what's the objective if we build something like this? What are we really trying to do? And that's to do things that we can't do with our conventional machines. Again, I'll go into more detail on Wednesday in terms of what two specific things you can do with systems like these, but just for now, as an overarching goal, there are things that we would really like to do, and we can't do them with our machines right now. And just to set the stage again, this is one question I hope will lead into that discussion later on. And with that, if Jeff Kirchmar is here, yeah, Jeff, here. We'll go ahead and go to the experiments part.